Are you guys ready for this? More trig identities. I know. I'm excited too. I know you didn't think life could get any better having the sum and difference identities formulas, but it does. Yay! We're going to identify some more. So in this section, we're going to look at cofunction, double angle, and half angle. So we'll just take those one at a time. The cofunction we've kind of already seen. We'll write those down and we'll do some stuff with them, and then we'll talk about double angle and half angle. I'll let you know right now, the ones that you will need to know from memory, there are only two of them. You're going to need to know the double angle formulas. Okay, so just kind of keep that in mind. I'll be giving you pretty much the rest of them. So let's talk about first the cofunction identities. We've actually talked about these already, but we talked about them in a way that really only worked for when we were in, remember when we first started out with trig, when we were brand new, and we were defining sine and cosine to be the ratios of sides of triangles, sides of right angles, sides of a right triangle, ratios of the sides of a right triangle. But now we know our world is more open than that, right? And we know more things. So we know that now we can take, sine, cosine, and tangent of any angle, not just acute angles. So now it's important to write these down, because then this tells us that that this works for any value of x. Okay, any real number. And we've kind of seen these before. I mean, if you think of these as acute angles like the x, then we know that, the sine of 30 is equal to the cosine of 60, stuff like that. So we know that if we have two complementary angles, that their cosines and sines are equal. But now this is actually true for any angle, any real number whatsoever. So what are cofunctions? The cofunctions, that's sine and cosine, are what we call cofunctions, because we can write these identities that relate these two functions together. Then tangent of pi over 2 minus x is the same as cotangent of x, or we can go the other way. The cotangent of pi over 2 minus any real number x is going to be the same as tangent. And you could prove all these. I'll prove one of them for you, but let's get these all written down first. And then secant, because sine and cosine are cofunctions, kind of makes sense that secant and cosecant are cofunctions, because those are just the reciprocal functions, right? Cosecant of x and then cosecant of, pi over 2. Goodness. Minus x is equal to secant of x. And let me, really quick, just because I know you're dying to know, let me prove this one for you really fast. This shouldn't take us very long. This isn't in my notes or anything, but I'm sure we can figure this out together. So let's prove that sine of pi over 2 minus x is equal to cosine. So just a quick thing about proving identities, because it's going to come up in the next section. How I want you to prove identities. When you prove an identity, when you prove a statement like this, you need to start with one side of the equation and show that it equals the other side. I don't want you working with both sides at once. That's kind of assuming that they're both true. I don't like that method. It's not as strong mathematically. You need to start with one side and prove that you can get to the other. So normally, and we'll talk about this in the next section though, normally we want to start with the side that's a little more complicated. So let's start with sine of pi over 2 minus x. And what I'm going to use is I'm going to use my difference formula. So remember sine of alpha minus beta, right? That was sine alpha cosine beta. I should have given myself some more room. Minus cosine alpha sine beta. So sine, cosine, cosine, sine. So I'm going to use this formula, except instead of having alpha and beta, I'm going to have pi over 2 and x. So I'm going to have sine of alpha, but alpha in this case is pi over 2. Times cosine of beta, but in this case that's x. Move this out of the way. Remember I'm giving you those sum and difference formulas, but you need to know how to use them. Take some of that pressure off, but you still need to practice with them. So sine, cosine minus cosine, sine. So cosine then of pi over 2 sine of x. And the great thing about this is a pretty easy one to prove. Cosine of pi over 2 I know is 0. Sine of pi over 2 is 1. So sure enough, I get 1 times cosine minus 0. That is also known as cosine. Smiley face. That's actually not how we prove something. We put a little box that say that we're done. The proof is finished, but I kind of like the smiley face. Wouldn't have gone over super well in graduate school, but you know, whatever. Okay, so those are my cofunction identities. We have a couple more that I want to add to this, so you might, well, let's just look at the next one. We're going to add a couple more, so in your notes, you might think about that. I'm going to add just a few more. What about if we have, let's look at sine of x. What if it wasn't pi over 2 minus x? But what if it was sine of x plus pi over 2? Well, what would this be? This would be sine x cosine of pi over 2. So I'm just saying, what would be the difference if I added the pi over 2 instead of subtracting my real number from pi over 2? So remember, it's sine cosine plus cosine sine. And so the interesting thing about this is, if you notice, I'm going cosine of pi over 2 is 0. And so actually when I take the sine of x plus pi over 2, same thing as the sine of pi over 2 minus x, I'm just going to get cosine out. And actually the way you can really see that, oh man, might be bad. This might be bad. It's okay. Sine is this, right? Sine goes through the origin. And what happens if I add that pi over 2? We talked about that. That's a phase shift, right? So here's pi over 2. And so what's going to happen if I add pi over 2? That's going to be a shift to the left pi over 2. So this point right here is going to go here, right? This point right here will be here. This point down here is going to be over pi over 2. This 0 is over pi over 2. That point's gone over. This point here comes here. That point there comes there. And so if I were to take sine and do a phase shift to the left pi over 2, if you notice, I'm going to get a beautiful function that looks like this, right? But you guys, what is that? That, my friends, is just cosine of x. Remember, cosine starts at 0, 1, goes through 0 at pi over 2, 3 pi over 2, 5 pi over 2. And so this identity really makes sense, because really if we just think of this as taking the graph of sine and shifting it to the left pi over 2, then we are going to get cosine. So to add to those cofunction identities, some more of those, more cofunction identities. Let's add to this, and I'm not going to prove every one of these for you. So the sine of x plus pi over 2, okay, is going to be cosine of x. We already found out what the sine of pi over 2 minus x is. What if we did the sine of x minus pi over 2 though? Right, what is that going to be? That's actually going to be just a negative cosine of x. Okay, couple ways you could think about that. Sine of x minus pi over 2, that's the same thing as the sine of an opposite of pi over 2 minus x. And because sine is an odd function, it'd be a negative of whatever the sine of pi over 2 minus x is, which is cosine x. So I told you I wasn't going to prove that, and that's not really a proof, but just in case you feel like you can't sleep tonight knowing why this is true, or do the difference formula, you'll see that that's true if you use the difference formula for sine. And then for cosine, I'm not going to prove these, or I'm telling myself I'm not going to prove these, but cosine of x plus pi over 2, that's actually going to be a negative sign, so they kind of switch. And then cosine of x minus pi over 2, remember cosine's an even function, so if we switch the pi over 2 minus x, it's going to give me the same thing, because when I take the cosine of negative x, it's the same as cosine of x. And so those are some more of the cofunction identities. So when you go to do some of these problems, like in the homework, when it's asking you to find these values of angles that are complementary to each other, you need to just like set out these cofunction identities, that you have them all in front of you, so that you're ready to figure out what how to use them and and what they all mean. So let's do one example, and I'll kind of show you the idea of this. Let me get rid of that. Okay, so quick example. So let's say, given that, this one's a little bit crazy, but given that, let's say that the sine of pi over 12, which we know we can find, right, using the sum and difference formulas, let's say that this is square root of 2, not say, it is 2 minus the square root of 3 all over 2, and then the cosine of this, right, is going to be square root of 2 plus root 3 all over 2. So because we know those, let's find the 6 trig functions, or the 6 trig values of 5 pi over 12. So why 5 pi over 12? Because 5 pi over 12 plus pi over 12, whoops, I needed a 12 there, is pi over 2, right? So let's look at kind of how we're going to do some of these. So if I wanted to find, let's say, let's start off pretty easy. If I want to find the sine of 5 pi over 12, I'm going to rewrite this as the sine of pi over 2 minus 5 pi over 12. Right? And if we got a common denominator, I hope that's pretty easy to see. I would multiply this by 6 over 6, so that'd be 6 pi over 12. Oh, I'm sorry, I'm messing this up. Sorry guys, I want to get 5 pi over 12. Sorry about that. So this is pi over 12, excuse me. So notice if I do pi over 2 minus pi over 12, right, that's 6 pi over 12 minus pi over 12, which gives me that 5 pi over 12 that I want. So now why did I write it like this? Because I know that the sine of pi over 2 minus x, and there are other ways that you could have done this, is equal to the cosine of x. So what is the sine of 5 pi over 12 going to be? It's going to be what the cosine of it is. So that's going to be 2 plus root 3 all over 2. Simple as that. Likewise, the cosine, right, of 5 pi over 12, okay, is just going to be the cosine of pi over 2 minus pi over 12. Okay, but remember that just equals the sine of whatever this value is right here, pi over 12, right, that value right there. And what is that? That's the square root of 2 minus root 3, I'm sorry, 2 plus root 3 all over 2. Nope, 2 minus. Oh man, I'm like out of it today. I'm not sure what's going on. I do know what's going on. I know what's going on. My son is not sleeping. That's what's going on. I have an 18-month-old son with a cold, and that's what's happening. He's not sleeping. So there's not enough coffee in the world to make me do this lecture correct the first time. Okay, so I hope that makes sense how we could do that. And there's a reason that I gave you 5 pi over 12, or gave you pi over 12 and asked you for 5 pi over 12. I could have given you 11 pi over 13, right, and asked you for another angle that would get us to the pi over 2. Or that'd be tough to do with 13, but you get what I'm saying. How do I find the other 6 trig values? Well, let's think about tangent. So these I might not go through completely, but tangent I know is just going to be, so now we're using some of our other identities. Tangent is just sine over cosine, right? So I'm not going to simplify all of this for you, but you can do that on your own. So if I do sine over cosine, the 2's cancel. And so for tangent, I would get 2 plus root 3, right, all over the square root of 2 minus root 3. I don't even need a special cofunction for that. I can just use the fact that I know that tangent is sine over cosine. So same thing with, if I wanted to find cosecant of 5 pi over 12, I'm going to just take 1 divided by sine of 5 pi over 12. So I would just take this and flip it. Same thing with that one, and I'll let you figure out how to rationalize that denominator. It's a little bit complicated, but I'm sure you can do that. And then secant, rationalizing the denominator is not really the purpose of this lecture. Same thing with cosine, or secant, excuse me, I would do 1 over cosine. So it's a pretty basic way of showing you how to use those cofunction angles. Okay, let's move on then to 2 of my favorite identities, I have to say, which 3, I guess, because there are 3 of them, are the double angle formulas. So here's our idea. So double angle formulas. What happens? Is there a way if I know the sine of, theta, how are sine of theta and sine of 2 theta related, right? I mean, we would want to maybe say a prayer to the math gods that, just like when you get to calculus, you're going to see this. Is this sine of 2 theta, right? This is what we're going to hope that's going to happen. Is the sine of 2 theta equal to 2 times the sine of theta, right? That's kind of what we're hoping to happen. One way you can see that this is not true, that's a bummer, huh? Is that look at if I take the sine of 60 degrees. Well, what is 60 degrees? 60 degrees is the same as the sine of 2 times 30 degrees, you guys. So is it going to be true that I just take 2 times the sine of 30? Would that make any sense? Well, I don't think so, because what do we know? We know that the sine of 60 is root 3 over 2, and we know that the sine of 30 is 1/2, and unless something changed last night while I was not sleeping, root 3 over 2 is not equal to 1, right? So it's not going to be as simple as just taking the sine of an angle and then multiplying it by 2. So we have to figure out something else to do, and that's okay. We can figure out something else to do, and actually it's going to be pretty cool to do this. So the way that we are going to, and this is absolutely something that I could have you prove maybe on a test. That would be pretty fun, wouldn't it? I don't know if you like, if you care about what I like or what I don't like, but when it comes to, you know, exams and having you prove something, this is one that I would kind of like. I don't know if you care. But let's say that I do have the sine of, what does it mean to have the sine of, and we'll just use x's because that's kind of what we're used to instead of thetas. But what if I had the sine of 2x? So I want to see, is there a way for me, based on what I know about maybe the sine or cosine of x, is there a way for me to figure out the sine of twice that angle? So if I know maybe that the cosine of 17 degrees, right, is a value, could I somehow figure out what the cosine of 34 degrees is just by knowing what the cosine of 17 is? And there actually is a way. So here's how we're going to prove this. I'm going to take the sine of 2x, and I'm going to realize, in case you didn't know this, 2x is x plus x. That's what it means to double something. Okay, and now what I'm going to use is I'm just going to use my sum formula. So my sum formula for sine says sine, cosine, cosine, sine. So sine, cosine, sine of the first, cosine of the second, plus cosine of the second times sine of the first. Even though the first and the second are exactly the same, I still am going to take that order. And so here's my double angle formula for the sine of 2x. I'm just going to put those two together, and we get 2 sine x cosine x. So remember, I'm not going to give you the double angle formulas, but I am giving you the sum formulas. So if you can just remember to do this, and you'll probably do it on the test anyway where you prove it, if you can just remember to do this, you can figure out what these double angle formulas are. So same thing with cosine. So this is pretty cool. So if I know what x is, if I want to find the sine of 2x, I just need to take 2 times the sine of x times the cosine of x. Okay, and we'll do some examples, of course. Likewise, if I want to figure out a formula or an identity for cosine of 2x, I'm going to think of that as cosine of x plus x. So what does cosine do? Remember, cosine, it does cosine, cosine, sine, sine, except it's the opposite sign, S-I-G-N. So I have cosine of x minus sine of x, sine of x. So what is cosine of 2x? It's cosine squared minus sine squared. Isn't that cool? And then tangent of 2x. If you remember back to the sum formulas, I don't think I proved those to you, but it was like tangent alpha plus tangent beta all over 1 minus tangent alpha, tangent beta. So if I substitute that with just x and x, we would have 2 tangent x all over 1 minus tangent squared x. Aren't these great? I love the double angle formulas. I just think they're so cool. So those are my double angle identities. Let's write those down kind of all together, and then we'll do some examples with them. Okay, so more formally, the double angle identities. Okay. Oh, that's not how you spell identities. Sarah sounded out identities. There we go. All right, so double angle identities. Sine of 2x is just 2 sine x cosine x. You're going to need to know these. And cosine of 2x. Now, cosine of 2x, we're going to mess with a little bit. So cosine of 2x is cosine squared x minus sine squared x. So you need to know that one for sure. But you also need to know how to get to some other ones. So think about if we replaced this sine squared of x, remember I know that sine squared of x is 1 minus cosine squared from the Pythagorean identities, and I would be taking that negative through, so I'd have cosine squared x minus 1 plus cosine squared x. If you notice, if I replace that sine squared with it, so what would I get? I would get 2 cosine squared minus 1. So that's another way of writing it. Or the other way we could have done this, let me get rid of some of this right here. What if I had replaced, what if I had replaced this cosine with 1 minus sine squared from the double angle, or from the Pythagorean identity? Here I don't have a negative or anything to take through, so I would just get 1 minus 2 sine squared. So the cosine double angle has kind of a couple options for us. If you don't, you don't have to memorize these necessarily. You do need to know cosine squared minus sine squared, and then you can get to the other ones by just replacing those, cosine squareds and sine squareds with the resulting Pythagorean identity, okay? And then finally, what did we get for tangent of 2x? Tangent of 2x was 2 tangent x all over 1 minus tangent squared. Let's do a couple examples, and then we just have the half angle formulas or identities to talk about. And then that's it. And then that's all we got. So pretty cool. So let's do a couple examples with these. Let me clear that out. So for example, let me get my notes out here. Sometimes I get a little cocky and try and do this without my notes, and that's not always the smartest. That's not the smartest thing to always do. Okay, so let's say that I know that the sine of some angle theta, I don't know what angle theta is, but I know that the sine of it is 3/5, and that theta is in quadrant 2. So I'm going to say that theta is between pi over 2 and pi, or I could just state that theta is in quadrant 2. Given that that is true, find the sine of 2 theta, cosine of 2 theta, and tangent of 2 theta. And I really cannot stress enough, you guys, that you don't just take 3/5 and multiply it by 2. That was that whole exercise that I showed you where we took the 30 and the 60 degrees, okay? You don't just take it and multiply by 2. We have to use the double angle formulas. And let's look at those double angle formulas and see what we're going to need. So we're given that sine is something. What else are we going to need? We're going to need cosine for sure, right? And then if we have cosine, we can find tangent. Honestly, if I have sine and cosine, I'm not using the double angle formula for tangent. I am just going to take sine divided by cosine. So I know I need cosine of theta. So I know that sine of theta. So this is the same thing that we've been doing for a long time in this class now. I know that the sine of theta is 3/5, and I know that I'm in quadrant 2. So if I graph theta, right? Oh, also state where this is going to be horrible English. Theta, 2 theta is. That's horrible. But what I mean by that is state what quadrant, in which quadrant does 2 theta lie. That sounds better, right? So I'm going to draw my triangle, right? Theta's in quadrant 2. Sine I know is y over r. And this is a 3, 4, 5 triangle because I'm lazy and I did not want to give you things with radicals. But I'm in the 4th quadrant. So what do I know about that 4? It must, excuse me, I'm in the 2nd quadrant. So what do I know about that 4? It must be negative, okay? So I know that the cosine of theta then is going to be a negative 4/5. And now easy peasy, I'm going to use my formulas. I know that sine of 2 theta is going to equal 2 sine theta cosine theta. Okay, so 2 sine theta cosine theta, that'll be 2 times 3/5 times a negative 4/5, right? There's my sine, there's my cosine. So what do we get? Negative 24/25. This number better be between negative 1 and 1. Remember, cosine and sine never go over 1 or less than negative 1. So there's sine of 2 theta. Let's look at cosine of 2 theta. So this is going to be cosine of theta squared minus sine squared of theta. All right, so parentheses are going to be important here, people. You must put that 4/5 in parentheses. I want to see the parentheses, or else I am taking off because it does not make sense. Okay, that negative has to be squared. So this is 16/25 minus 9/25, which I believe is what, 7/25? that right, guys? Yeah. So there's my sine of 2 theta, cosine of 2 theta, and finally tangent of 2 theta. Now listen, if you want to do the double angle formula, I get it, because when you get something new, right, you just want to use it. So you're welcome to use the double angle formula. Or you guys, you know, what is tangent of 2 theta? It's sine of 2 theta over cosine of 2 theta, which in this case, if I take sine and I divide it by cosine, I would get the 25s would cancel, and we would get a negative 24 over 7. Okay, so there are my 3 values for cosine, sine, and tangent of 2 theta. So this last question right here, so pretty easy. Well, maybe not easy, but state where 2 theta is. What I really mean there is, in which quadrant does 2 theta lie? So, you know, let's think about being in quadrant 2. I mean, hypothetically, the smallest theta could be is 90 degrees, and the biggest theta could be is 180. So if I multiplied all of this by 2, right, that means theta is going to be between pi and 2 pi. Well, that's not a quadrant, people. That just tells me that I'm in either here or here, right? Oh, that should be a 2 theta. So how am I going to pick if it's in the 3rd or 4th quadrant? Well, I'm going to look at the signs of my sine, cosine, and tangent. Notice sine is negative, cosine is positive, and tangent is negative. So based on my quadrant system, I don't even actually have to put it down to 2 quadrants. Where is cosine the only one that's positive? Well, if all students take calculus, the only one that's the only place that cosine is the only positive one is going to be in the 4th quadrant. So I know that 2 theta is in quadrant 4. Okay, that has to be true based on the signs, S-I-G-N, positiveness or negativeness of my sine, cosine, and tangent. Those are so fun. I love doing those. I just love them. Let's do one more quick one where we're not actually having the angle, but we talk about simplifying like we had before. Like, what if I wanted you to do something like simplify, I think on your homework, they have you do like cosine of 4x. Let's do sine of 3x. So something like simplify sine of 3x. Well, my first argument would probably be it's as simplified as it can go. But that's not what they want you to do, right? So let's look at sine of 3x. Their goal for you in this is to use your sum formula and your double angle formula together. So the trick for this one, and really maybe this, I should have said like expand this. So I'm going to rewrite 3x as x plus 2x, and then I'm going to use my sum formula. So even though I'm not making you memorize the sum formula, I bet you're going to memorize it anyway. Unwillingly, because you're using it so much. So I'm going to take my sum formula, sine, cosine, cosine, sine, and I'm just going to mess with this a little bit. So the sine of x I can't really do anything with. What about cosine of 2x? So I sure can do something with that. That's cosine squared minus sine squared. I actually don't quite know what's going to happen here. And then since I didn't give myself room, I'm going to move that to the bottom there. Plus, let's see, I have cosine x times, well, what is sine of 2x? That's 2 sine x cosine x. This looks kind of interesting. Let's keep expanding, see what we get. So if I bring this through, so I get sine x cosine squared x. So I'm distributing. Minus sine cubed x, and then here I'm going to have plus 2 sine x cosine squared x, right? That's kind of neat. So what else can I do here? Well, these guys are like terms, if you notice. They each are a sine x cosine squared. So I would get 3, there are 3 of them now, sine x cosine squared x minus sine cubed x. Now, there's not much else I can do with this. I could take a sine of x out, and while that might be fun, which we could do, I would actually, your answer, if you put your answer as this, I would absolutely take this. This would be fine. There's just not a whole lot I can do from here. I suppose I could get everything in terms of sine. I could rewrite this in terms of 1 minus sine squared. But honestly, I would accept this answer. I would accept this answer. If you rewrote cosine squared as 1 minus sine squared and then took the 3 through it and combined like terms, which I think you get like 3 minus 4 sine squared x at the very end. I would accept that times sine. Sometimes it's hard with these when they just say simplify these expressions. It's hard to figure out how far you're supposed to go. Luckily in your homework there's multiple choice. I'm not giving you multiple choice on the test, but just go as far as you can. When you feel like you've simplified it or expanded it as much as possible, just go ahead and stop. Okay. I don't know, one more. Yeah, and then we'll talk about half angle and then we'll call it good. Let's factor this. So this one is kind of a classic one. I really love this one here. Something like this, cosine to the fourth x minus sine to the fourth x. So what I'm going to look at this as, cosine to the fourth is really cosine squared squared. Same thing with sine to the fourth. That's sine squared squared. That's just fun to say. I don't care who you are. And this, my friends, is a difference of squares. We actually already saw this one. I believe we did this one already when we did the Pythagorean identities. But the great thing about this one now that we know the double angle formulas, right, is that this one goes to 1. And what is this right here? That's cosine of 2x. So that guy right there, cosine to the fourth minus sine to the fourth, is actually exactly the same as cosine of 2x. And that's it. Okay, you guys, we have the last thing to get to are the half angle formulas. So I want to talk about the half angle formulas really quick. And then we will we'll call it good. So what I'm going to use to talk about these half angle formulas is I'm going to use these facts right here to find the half angle formulas. So the half angle formulas are all going to come from the fact of these guys right here. So just kind of hang with me with this and then we'll write these down. I'm going to give you the half angle formulas on the test. They're ones that I have trouble remembering, but the double angle ones are quite useful when you get to calculus and stuff if you can recognize the double angle. But half angle, we use half angle quite a bit honestly in calculus, but let's just kind of see how we're going to do this. So first of all, let's look at this relationship here. I know that 2 cosine squared x minus 1 is equal to the cosine of 2x. So what I'm going to do here is I'm actually going to solve for cosine. So if I add 1 to both sides, I get 2 cosine squared x equals cosine of 2x plus 1. Okay, I'm going to divide by 2. So I get cosine squared of x equals cosine of 2x plus 1 all over 2. And now I'm going to square root. Remembering that when you square root, you guys, when you square root, if you're bringing in a square root that was not there in the first place, you must put a plus or a minus. Okay. So this is going to be a little bit weird, but what I'm going to replace, I am going to take this x right here. Notice this x is really just half of 2x. Do you agree with that? Right? Notice x is really just half of 2x. So I'm going to rewrite this as, well, what if I just replaced all of this with x, right? Then what would this guy be? That would be half of it. And that's why they're called the half angle formulas, okay? So what we get for these half angle formulas is I get the cosine of x over 2 is plus or minus the square root of twice that. So that'd be just cosine of x plus 1. I'm really just making a substitution here. All over 2, and you can see why I'm going to give these to you. And we're going to do some examples that you're going to see are going to be really nice. But what I've done again is that notice this number here is just half of this. So if I replace this guy with the actual x, then we have cosine of x over 2. Now you would do a similar argument for solving for sine. I would do the same thing. I would solve for sine and then I would replace the x over 2. So let me just write these down for you, and then I really want to spend time doing an example. Okay, so these are called the half angle identities. I don't know. Oh, there are dashes in there. Sorry. I just put double angle. I don't know why there are hyphens. Someone with well, I have a father and a sister who are both English teachers, so maybe I should ask them why there's that dash. But okay, so sine of x over 2. Again, they're called half angle because we want to find the sine of half of that angle. So if I know that the sine of, you know, 64 is something, then I can find the sine of 32. I can find half of that. And the plus or minus that we're going to look at is we're going to decide that plus or minus based on wherever the x over 2 is going to be. So the last one was 1 plus cosine of 2x. This one is going to be 1 minus cosine of 2x. So the sine one is minus all over 2. Okay. Cosine of x over 2, which we saw was the cosine of, oh, I shouldn't have 2x. I'm so sorry. I was caught up in what I was proving. This is just x. Remember, this value is always twice this value. Same thing here. But instead of having minus, I'm going to have plus. So this is 1 plus cosine of x all over 2. And then the tangent one is kind of cool, actually, because the tangent one, again, I'm going to give these to you, but you need to know how to use them, is I would divide these two. The 2's would cancel, so I'd still have plus or minus 1 minus cosine of x all over 1 plus cosine of x. And you guys, if you get bored, you should rationalize the denominator, and you will see some really cool stuff is going to happen. Rationalize the denominator and then rationalize the numerator. So what I mean by that is multiply by 1 minus cosine x on top and bottom and see what happens. And then same thing, do 1 plus cosine x on top and bottom and see what happens, and some really cool stuff happens. You end up getting some perfect squares. So I would get on top sine of x and then 1 plus cosine x. I'm sorry, don't rationalize. No, rationalize, that's what I mean. It ends up rationalizing the top and the bottom, it doesn't matter. This is 1 minus cosine x over sine x. I'm just not gonna, we're already at 36 minutes, so I'm not gonna take the time to show you that, but it's really cool. You should do it. All right, so let me show you a quick example. So let's find maybe 2 examples. The exact value of 75, whoops, not 75 degrees, of cosine of 75 and sine of 75. Okay, so we know, okay, I'm going to say using the half angle. Half angle identities. Okay, so we know we know what these are, right? We saw these before. We could use a sum formula. We could do 30 plus 45. We could do a sum formula easily with this. But what if I wanted to do well, I want to do the half angle. So if I want to find the cosine of 75, so here's the trick. Okay, what you always want to do when you're doing the half angle identities to find these exact values is you actually want to double the 75. So 75 is really just doubled 75, right? 150 divided by 2. That's true. Yes? So 75 degrees is really 2 times 75 divided by 2. So 150 divided by 2. Now, why is 150 a number that I can work with? Because its reference angle, you guys, is 30 degrees. And if I know its reference angle is 30 degrees, then I know I can use this. Now, 75 degrees, what quadrant is 75 degrees in? That's the second quadrant. Cosine is negative in the second quadrant. So I'm going to pick the negative for my square root. So now I'm going up here and I'm working with my half angle formula. I'm going to need some more room here. And then I'm going to have 1 plus the cosine of, so now look at this, that x right here corresponds to this x right here. And so that's what I'm going to put in here when I use my half angle. This is going to be 150 degrees. That's going to correspond here all over 2. So remember a couple of things here that I want to make sure you caught. This negative right here, how do I know I choose the negative? Because 75 is in quadrant 2, and I know I'm taking the cosine of it, so I know that the cosine of that is going to be negative in the second quadrant. Cosine are your x values. And then this, I just take twice 75, and I rewrite it as twice 75 divided by 2, and then that 150 is the number that I put right here. Okay, so let's rewrite this on and give ourselves a little bit more room. And all right. So what did I have again? We had the cosine, make that a little brighter so you can see it, right, of 75 degrees then was the opposite of the square root of 1 plus the cosine of 150 degrees all over 2. So to find this exact value, I got to find the cosine of 150 degrees. So you could use your unit circle if you want. What I like to do is say, okay, here's 150 degrees, right? What is my reference angle? My reference angle is 30. I know that the cosine of 30 degrees is root 3 over 2, but I'm in the second quadrant, so the cosine of 150 degrees is going to almost be that, but I'm in the second quadrant, so it's negative. Okay, so write big, not only so you can see what you're doing, but so I can see what you're doing. I'm going to have 1 minus root 3 over 2, and this is all going to be over 2. And now we got to simplify that sucker. This is a complex rational expression. What is the denominator that I'm dealing with that's causing that problem? It's a 2. So multiply everything on top and everything on bottom by that 2. Make that square root come over. Okay, make sure this sucker distributes to each term. So I get a negative square root of 2 minus, these 2's cancel, right? Root 3 all over 4. And now I'm just going to break up that square root. So I get a negative of the square root of 2 minus root 3 all over 4. Okay, that's a little bit crazy, I know. But that's it. That's the exact value of the cosine of 75. I know we got numbers that looked a little bit different when we did the sum and difference formula, but they will be the same. Okay. For sine, you're going to do the same thing, right? Except for sine. So sine of 75 degrees, if I'm using the half angle formula, this will be the sine of 150 divided by 2. Sine in the second quadrant is positive, so I'm going to take the positive one, right? Positive. Oh, I'm so sorry. Oh my gosh, you guys, I bet you're yelling at me. I was thinking of 150. 75 degrees is in the first quadrant. Oh no. Have you been yelling at the computer for the last 10 minutes? I blame Leo, that's my son, because he was up all night because he has a cough. I am so sorry. This is not in quadrant 2. Oh, if you would like verification of my math degree, I promise I'll send you my transcripts. I do hold a master's degree in mathematics, I promise. I am so sorry. That's all positive because we're in the first quadrant. Oh, how embarrassing. What's different with the sine? This is going to be 1 minus the cosine of 150 degrees. So same idea, right? We're going to have the same method basically, but it's going to be minus root 3 over 2. So what happens here then is when cosine of 150 is a negative, so this is going to be minus a negative root 3 over 2. Okay, all over 2. This becomes plus. So basically we get the same thing except we get a plus sign in there. I am so embarrassed with that 75. Those should all be positive. Cosine of 75 degrees is positive. Wow. Wow. They should make me give my degree back. I'm so sorry about that. So I hope that kind of makes sense. You can use that for tangent. Also, we could just do sine divided by cosine. Or honestly, for tangent for this one, man, it would be... tangent would be quite easy here. If we wanted to find, okay, I promise I'm about done talking. You guys are probably out of here anyway. So tangent is 75 degrees. That would be the tangent of 150 degrees, right? All over 2. And so that means I would plug it into one of these. So that would be the sine of 150 degrees all over 1 plus the cosine of 150 degrees. That'd be pretty easy. Sine of 150 is 1/2. It's positive because sine is positive in the second quadrant. Cosine of 150 is a negative root 3 over 2. So that's pretty nice. Multiply everything by 2 over 2. And we get 1 over 2 minus root 3. And then you could rationalize the denominator by multiplying by 2 plus root 3. I think I'm going to be done talking because I feel like I made that error right there. And so I should be done. When Leo grows up, I'm going to make him watch this YouTube video and be like, look what you made me do because you didn't sleep last night. Maybe that would put him to sleep. Maybe I should have him watch this video to help him sleep. It's probably put you to sleep if you're still listening, man. Good on ya. Okay, if you have questions, well, please look at the fun sheet and look at more examples of this half angle formula. I didn't break this into 2 lectures, but I know seeing lots of examples helps. So if you need more examples, if you need me to record more examples, just let me know.